cut off the border and cut out every box. Well, cut all the dotted lines. Put it that. Okay, so thermodynamics. What does thermo mean? Heat. Dynamics. All right, change. Let's start off with a few basic concepts. These are things you already know. We're just going to give it words. Heat transfer. Okay? So heat moves from the blank object to the blank object. So picture two objects. One is cold and one is hot. What direction does the heat move? The heat energy moves from the hotter object to the colder object. So, if I set my warm hand on a cold desk, the heat moves from my hand to the desk, and after a few moments, if you take your hand off, you'll feel that the desk is actually a little bit warmer where your hand was than the rest of the desk. Does that make sense? So that heat energy moves from the hotter object to the colder object. We've got red and blue. In our society, in our culture, what do red and blue mean?
Hot and cold.
So, give yourself a little reminder there. Right, hot in red. Right, cold in blue. I'm going to glue it in after I've written on it, just so it's easier to write on. Okay? So we have here a hot object. You can tell by the little thermometer up there. Okay? Nice and high. So it's a hot object. And heat transfers, and we will end up with heat transfers to a cooler object. Thermal equilibrium. Another concept you already know, but you probably never thought about. We've got hot water and 20 degrees, and we put in that hot water a cold, we'll just say it's a rock. Make it easy. A cold rock. Okay? So hot water, and we plop a cold rock into it. And we give it lots of time. What will eventually happen?
It will get the same.
The same what?
Temperature.
They'll have the same temperature. The water and the rock are both 15 degrees Celsius. Okay? Notice the water has cooled down and the rock has warmed up, and now they're the same temperature. So, heat energy continues to move until both objects are the same temperature. That is thermal equilibrium. Okay, remember we said equilibrium means balance? Well, the heat energy is now balanced between the two objects. Alright, so if we can achieve this thermal equilibrium, we have heat transfer, heat energy moves, and then we achieve thermal equilibrium where we have a balance in the thermal energy between objects. That tells us that heat is able to move from one place to another, from one object to another. There are three methods of heat transfer: conduction, convection, and radiation. And we are going to discuss each one of those in detail. Starting with conduction, let's write on it first and then glue it in later. So, conduction. Conduction is heat transfer through solid objects. Okay? That means the heat is transferring through that object from one end of the object to the other. Okay? Or conduction is the transfer between two objects that are touching. Okay? The thermal energy passes from molecule to molecule. So it passes from molecule to molecule through direct contact. All right. Flip back to page 30 in your journal. Back to page 30 in your journal, energy types and transformations. Thermal energy, find it. What category of energy does thermal energy fall under? Kinetic energy. Okay? Thermal energy is a form of kinetic energy. Kinetic energy is about things in motion. Okay? If you read thermal energy here, it says heat energy, the end product of many transformation, the result of friction, fire, increased temperature. Okay? But what's actually doing the movement? What is moving? All right. The molecules are moving. So write down here a little note. Molecules vibrate. And that's what we're measuring when we measure the temperature of an object. We are measuring the average movement of the molecules in the object or in the substance. Conduction, that heat energy is transferred from one molecule to the next through direct contact. So we have a hand, and you put an ice cube on it. Heat is transferring from your hand to the ice cube and causing the ice cube to melt. We have a pot, I'm going to go ahead and use the red there, sitting on a stove. The pot and the stove are in direct contact with each other. Okay? The stove is going to move its heat to the pot. And they're directly touching each other. This third one, okay, you might want to glue in the paper so it doesn't move because we're going to have to write off the paper. The third one is just one single solid object. Okay, so we're just going to call this a metal bar. Okay, that metal bar, one end, we have nice hot fire. On the other end, we have cold ice cube. This end of the bar, yes? Yes.
Thank you.
With the metal bar, one end is hot, the other end is cold. And if you could measure the temperature at different points along the bar, you'll find that it's the hottest nearest the flame, and it's a little bit cooler and has less and less heat the further it moves from the flame. The closer you get to the ice cube, the colder the temperature is. So that heat is transferring down the length of the metal bar. Eventually, the ice cube will melt, and that heat would keep transferring, and all of those temperatures would rise at the same time. Next, we have convection. Again, I'm not going to write on it until we're finished. I'm not going to glue it in until we're finished writing on it. Convection. Heat transfer through the moving currents of fluids. Okay? The moving currents of fluids. Here's a great visual example for currents. This is rheoscopic fluid. All right? You can actually see the currents flowing in that bottle. If I tip the bottle, you can see how those currents change. Okay? So that helps you visualize the currents flowing in a fluid. Remember, fluid can be liquid or gas. Currents of fluids. First thing to note, with fluids, Everyone usually thinks, oh, liquid, of course, water. Currents and fluids are water. Well, fluids apply to more than just liquids. Fluids applies to liquid and gas.
Gas?
Gas, as in like the air we breathe.
Oh.
That can also flow. It can also be a current. Here's the most classic example of convection. We have a pot of water sitting on a hot stove. That hot stove is our heat source. If you're a water molecule in that pot and you're at the bottom of the pot, you are very near the heat source. Molecules near the heat source are going to be very hot. And if they are hot, they're moving faster, they're vibrating faster. And when molecules move faster and vibrate faster, they spread apart. And they become, therefore, less dense. Less dense substances will rise. So hot means the molecules are less dense. Therefore, they rise. Now, when they get to the top, they are near the surface and they will release heat energy to the environment, where they will therefore cool off and become less hot. And when they're less hot, they are more dense. Resulting in them sinking. Colder means more dense. Therefore, they sink. And then the process repeats itself. Those colder molecules have now returned to the heat source where they heat up again and become less dense, therefore they rise. Go to the surface where they release heat energy to the environment, decrease their temperature, become more dense, and therefore they sink. And you end up with this circular motion of the hot fluids rising and the cold fluids sinking, and that is convection. So over here, write a little note. If you need to glue that in, because you got it right off the edge, that's fine. Hot fluids rise because they are less dense. So what about cold fluids? Cold fluids sink because they are more dense. Hot fluids rise because they are less dense. And you end up with that circular motion. Okay? Convection is about that transfer of heat through the currents. Now, this is an example of liquid. What about an example of gas? I moved here in June, and it's a summer day. I'm at home. I need to get something out of the car real fast. I didn't want to go find my shoes, so I opened the door and just like, I'll just run real fast to the car. I get 3 steps out the door. I start screaming and run back inside. Why?
It's super hot on the pavement.
Yeah, my feet were being fried. The heat of the sun is absorbed by the ground. And so the ground is actually much warmer than the air around. Okay? In the summertime, the heat, the ground becomes so hot. If I take an egg, I crack it on the sidewalk, it will cook here in Laredo.
What about your shoes?
Okay? But if I crack an egg into a pan and I'm just holding it in the air, it won't cook. So the ground is actually a heat source, all right? When it's been in the sun for a really long time, the ground is actually a heat source. So all of the air right next to the ground is actually quite warm. So little red dots to represent warm air molecules. Well, what happens to warm fluids? Because gas is a fluid? What happens to warm air molecules? They rise. All that hot air moves upward. Well, if you're in a pan, it gets to the top and it just does a circulating thing in place. Well, we're not isolated. Our atmosphere is not isolated that much. So instead of just circulating right here, it sucks in cooler air from far away. So, for example, let's say this is Laredo, and it sucks in cool air from Corpus Christi.
Like today was cold in the morning.
So wind is what is generated. Wind is just air currents, cold air currents being sucked in because hot air is rising someplace else. Okay? So in the summertime here in Laredo, there's always a gentle breeze. There's always air in the summertime in Laredo. The flags are always waving just a little bit because of this. That hot air is rising and we're always sucking in cool air because we are about the hottest place around. The weather is caused primarily by convection, the movement of hot and cold air. Now let's talk about radiation. Take your scissors. We're going to cut the pictures off the bottom. The sun and earth, that's one picture. So separate that. The two t-shirts stay together. So you can cut that. We're going to do this all on the oops page. Because oops, it didn't fit. Radiation is the third way that heat can travel. That heat transfers through infrared. Electromagnetic radiation. When have you ever heard infrared before? In every class, someone says something about black ops. In black ops, when you're using infrared, at nighttime.
Yeah.
All right? When your eyes can't see anything, you look through infrared goggles, and now you can see pretty much everything. What you are looking at is the heat coming off of everything. The heat that everything is radiating off. Okay? So, there are some animals that have infrared vision. Owls. What's so different about owls? When you learned about owls in elementary school, another cool thing about owls, when are they awake? At night. They're nocturnal. So picture this. Picture this. Owls. You're an owl and you're trying to find a mouse in the grass in the dark. Good luck. Unless you have infrared vision. If you have infrared vision, that mouse glows in the dark. Because things that are warm are bright. So any warm-blooded animal is bright. It's like a little light bulb. You can even see it under the grass. Okay? So, heat transfer through infrared electromagnetic radiation, you're seeing heat energy coming off of that mouse. Well, you're not. The owl is. Okay? Radiation does not need a medium to travel. Medium means a solid, a liquid, or a gas. So, conduction. That's when we're talking about heat traveling through solids or from one solid to the next. Convection. That was about fluids and gases. Radiation, it doesn't need a solid or a liquid or a gas to travel through. It can travel through outer space where there is nothing out there. When we have a place where there's nothing there, we call it a vacuum.
Vacuum?
Mm-hmm. Infrared radiation can travel through a vacuum like outer space. Okay, it doesn't need a medium. When it does pass through a medium, all right, it doesn't pass through all mediums, but when it does pass through a medium, we describe that medium as being transparent or translucent. What does it mean when something is transparent? You can see through it. So think about this. Solid liquids and gases. Solid objects. The wall is a solid object. Can I see through the wall? No. All right. But what is a solid object that I can see through? Glass. It's a solid object, but yet I can see through it. Ever thought about that?
Wow.
All right. Now, there are some things that you can't see the details, but some light still gets through. We call those translucent. Lucent meaning light.
Oh, like curtains?
Curtains. Very good. Glue that in. The top of your oops page. Okay. Radiant heat travels in all directions. When we were talking about conduction, it's traveling whichever direction the colder object is. When we're talking about conduction. When we're talking about convection, the hot fluids rise and the cold fluids sink. Okay? So the hot fluids goes up. With radiation, it travels in all directions. So the picture here of a campfire, you can stand next to a campfire and feel the heat coming off of it. Okay? Now, have you ever noticed if you put something above the campfire, it's even hotter? Because that's not only the radiation, but also the hot air, the convection. So you get extra amounts of heat going upward. Okay? But you can still feel heat to the side with radiation. All right? The stove here, the heat comes off in every direction. If I turn the stove on in the kitchen and I put a pan on top of it, and I heat up the pan and the water in the pan, the rest of the kitchen still gets warm because that heat radiation goes in every direction. All right, black t-shirt, white t-shirt. We all live in Laredo. So, for the most part, when I ask you, which is the better one to wear in the summertime, you all know that answer. Why is the black so uncomfortable in the summertime? Black,
attracts the sun.
it absorbs. Whatever sunlight hits it, it absorbs the radiant energy. What about the white t-shirt? If black absorbs radiant energy, very good. White reflects radiant energy. So if you ever notice in the summertime, if you're standing there having a conversation outside with someone who's wearing an all-white shirt, you kind of like blink, 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 you kind of squint a little bit because their shirt seems so bright. Because all of the sunlight that's hitting it is reflecting right back in your eyes. Our last picture. We have a picture of the sun. There's a lot of different types of radiant energy that comes from the sun. But all of the energy we get from the sun is radiant. Okay? Infrared, that's the heat energy we get. Visible and ultraviolet, we'll talk about those later when we talk about the whole electromagnetic spectrum. But the sun, all of the heat we get from the sun comes through us by radiation. Because there's nothing between us and the sun. There's no solid, there's no liquid, there's no gas, so it can't get through us through conduction or convection. The only option is radiation. Okay? So the sun is actually an amazingly perfect example of radiant energy, radiant thermal energy, because that's the only way its energy can get to us. Okay? So that is the basics of thermodynamics. Conduction, convection, radiation, the three ways which heat can travel.